So we just talked about the force law to describe the interaction between a proton and an electron. You told me that when the distance went to infinity, the force went to 0. What happens instead when the distance goes to 0? What happens to the force? Yeah, so the force actually goes to infinity, and specifically, it goes to negative infinity. Infinity is the force when we're thinking about it in our brains. Negative infinity is when we actually plug it into the equation here. And the reason is the convention that the negative sign is just telling us the direction that the force is coming together instead of pushing apart. So we can use Coulomb's force law to think about the force between these two particles. And it does that. It tells us the force is a function of that distance. But what it does not tell us, which if we're trying to describe an atom we really want to know, is what happens to the distance as time passes. So r is a function of time. But luckily for us, there's a classical equation of motion that will in fact describe how the electron and nucleus change position or change their radius as a function of time. So does anyone know which classical law of motion that would be? Yep. So it's going to be Newton's second law, force equals mass times acceleration. Those of you that are quick page turners have a little one-up on answering that. And that tells us force as a function of acceleration. We want to know it, though, as a function of radius. So we can just take the first derivative and get ourselves to velocity. So force is equal to mass times dv dt. But of course, we want to go all the way to distance, so we take the second derivative, and we have this equation for force here. And what we can do in order to bring the two equations together is to plug in the Coulomb force law right here. So now we have our Coulomb force law all plugged in here, and we have this differential equation that we could solve if we wanted to figure out what the force was at different times t or at different positions of r. So all of you will have the opportunity to solve differential equations in your math courses here. We won't do it in this chemistry course. In later chemistry courses, you'll also get to solve differential equations. But instead, in this chemistry course, I will just tell you the solutions to differential equations. And what we can do is we can start with some initial value of r. And here I write r being 10 angstroms. That's a good approximation when we're talking about atoms, because that's about the size of an atom. So let's say we start off at the distance being 10 angstroms. We can plug that into this differential equation that we'll have and solve it. And what we find out is that r actually goes to 0 at a time that's equal to 10 to the negative 10 seconds. So let's think qualitatively for a second about what that means or what the real meaning of that is. What that is telling us is that according to Newtonian mechanics and Coulomb's force law, is that the electron should actually plummet into the nucleus in 0.1 nanoseconds. So we have a little bit of a problem here. And the problem that we have is that what we're figuring out mathematically is not exactly matching up with what we're observing experimentally. And in fact, it's often kind of difficult to experimentally test your mathematical predictions. A lot of people spend many, many years testing one single mathematical prediction. But I think all of us right now can probably test this prediction right here. And we're observing that, in fact, all of us and all the atoms we can see are not immediately collapsing in less than a nanosecond. So just if you can take what I'm saying for a moment right now, that in fact this should collapse in this very small time frame, we have to see that there's a problem with one of these two things, either the Coulomb force law or Newtonian mechanics. So what do you guys think is probably the issue here? So it's Newtonian mechanics. And the reason for this is because Newtonian mechanics does not work on this very, very small size scale. As we said, Newtonian mechanics does work in most cases. It does work when we're discussing things that we can see. It does work even on things that are too small to measure. But once we get to the atomic size scale, what happens is we need to be taking into account the fact that matter has these wave-like properties. And we'll learn more about that later, but essentially classical mechanics does not take that into account at all. So we need a new kind of mechanics, which is quantum mechanics, which will accurately explain the behavior of molecules on this small scale. So as I mentioned, the real key to quantum mechanics is that it's treating matter not just like it's a particle, which is what we were just doing, but also like it's a wave, and it treats light that way too. The second important point to quantum mechanics is that it actually considers the fact that light consists of these discrete packets or particle-like pieces of energy, which are called photons. And if you think about what's actually happening here, this second point, that light consists of photons, is actually the same thing as saying that light shows particle-like properties. But that's such an important point that I put it separately, and we'll cover that separately as we go along.